We'll now discuss the span of a set of vectors. And before we do this, we'll talk about what vectors mean graphically. If I consider a vector like 2, -5, we can also write this in parentheses as 2, -5. So we can also write it as an ordered pair. And we can do this with all vectors with 2 entries. We can write them as ordered pairs. Therefore, our vectors with 2 entries correspond to our two-dimensional coordinate system. And we denote this two-dimensional coordinate system by R2. In general, if we have vectors with n entries, then we can have an n-tuple that corresponds to Rn. So this does give us a graphical way to represent these. We can represent these as points in a plane. Next, we'll talk about what a linear combination is. We assume we have m vectors in Rn, so we have m vectors with n entries each. They will denote by a1 through am, and we will also assume we have these scalars c1 through cm. Then a linear combination of these vectors would be something written by c1 a1 plus c2 a2 all the way up to cm am. This is a linear combination of a set of vectors. We multiply each vector by a scalar, and then we add all of them up. Here I have a set of 3 vectors, a1, a2, and b. And I want to know, is b a linear combination of a1 and a2? That is, I'm going to look for scalars such that c1, a1 plus c2, a2 is equal to b. Since I know a1 and a2 and b, well, this just becomes a system of equations. My coefficients come from my vectors a1 and a2. And on the right, I have my constant vector. And we want to row reduce this and see if it has a solution. We already have a 1 in the first row, first column, so we'll work on getting zeros below it. For the first one, I need to do -2, row 1 plus row 2. When I do this, that gives me -2 plus 2 is 0, -4 plus 0 is -4, and -4 plus 8 is 4. To get the 0 in the third spot, I need to do -3 row 1 plus row 3. So -3 plus 0 is, or -3 plus 3 is 0. -6 plus 9 is 3. And then finally, -6 plus 3 is -3. The next thing we want is a 1 in the second row, second column. And we can do this by multiplying the second row by -1/4. That gives me a 1 and a -1. We'll now try to get zeros in the rest of that column. To get the first one, I will do -2 row 2 plus row 1. That would be 0 plus 1, which is 1. -2 plus 2, which is 0. And then for the last entry, 2 plus 2, which is 4. I should also do 3 row 2 plus row 3. And I can see that that gives me 0, 0, and 0. So, is this a linear combination? Yes. In fact, we can see that we have 4a1 minus 1a2 is equal to my vector b, because I did have a solution that was given by 4, -1. We do have this theorem about linear combinations that says a vector b can be written as a linear combination of a set of vectors a1 through an, if and only if there is a solution to ax equal to b. And we can see how this was used in our previous example. I had a vector b, and I had two vectors a1 and a2, and when I tried to solve to see if b could be written as a linear combination, I was actually looking at this system of equations here. Next, we'll define the span of a set of vectors. If I have a set of n vectors, a1 through an, this here is how we denote the span of a set of vectors. The span of a set of vectors is all of the possible linear combinations of these vectors. As a real-life example of the difference between a span and a linear combination, we can think of a computer or a TV screen and think of a single pixel. A linear combination would be what color you see at this moment, which is going to be some combination of red, green, and blue. The span of that pixel would be all possible colors that it could be, depending on what you're displaying on the screen. Let's consider these three vectors, and I want to describe what the span looks like. So I'm looking for anything that can be written as a linear combination. And here we are writing down just the definition of a linear combination. And this time I'm trying to find b. I want to know what vectors b I could put into this in order to get a solution. In order to do this, I'm going to set up a matrix. So I have 1, negative 4, 12, 1, negative 2, 0, and negative 1, 2, negative 3. And then in my augmented column, I don't know what this is. This is what I'm looking for. And we'll just say ABC and get some condition on these vectors b. We already have a 1 in the first row, first column, so let's work on getting zeros underneath it. The first thing I need to do is do 4, row 1 plus row 2. That would be 4 minus 4 is 0. 4 minus 2 is 2. Negative 4 plus 2 is negative 2. And then here we would have 4a plus b. For the third row, I need to multiply by negative 12. So I would have a 0, a negative 12. In the third spot, that would be 12 minus 3, which is 9. And then I have c minus 12a. My next step would then be to get a 1 in the second row, second column. However, I'm actually not going to do that because I'm not quite ready to introduce fractions. Instead, I'm going to work on getting a 0 underneath that spot. And we can see right now in the second row, I have a 2. The third row has a negative 12. So if I do 6, row 2 plus row 3, that would give me 6 times 2, which is 12, minus 12 is 0. I would also have 6 times negative 2, which is negative 18, plus 9, which is negative 9. And then here we would have 6 times 4a plus b plus c minus 12a. And that would give us 12a plus 6b plus c. And the main thing we wanted to do here was look for a row of zeros, and we actually don't have one here. Therefore, the span of these vectors is all of R3. Because it does not matter what A and B and C are, I will always have a solution because I have a pivot in every single row. The theorem we just demonstrated with that example says that a vector B is in the span of a set of vectors if and only if there is a solution to AX equal to B. So in order to figure out if something's in the span, we want to see if that system of equations has a solution. In our last example, it didn't matter what our vector B was, we would have a solution. Therefore, the span was all possible vectors.